Black holes, regions of space-time where gravity is so intense that nothing, not even light, can escape. Once considered purely theoretical, recent advancements have brought us closer to understanding these cosmic enigmas. Join us as physicist Brian Cox shares the latest progress in unraveling the mysteries of black holes.
We have two photographs, which are radio telescope photographs.
Right.
One of the one in the centre of our galaxy, which is a little one. It's called Sagittarius A star. It's a little supermassive black hole. So it's about 6 million times the mass of the sun, which makes it a little supermassive. And then there's another one, the first photo that was taken. It's a collaboration called Event Horizon. And they took a photo of one in the galaxy M87, 55 million light years away. That thing is around 6 billion times the mass of the sun. I mean, imagine that, 6,000 million times more massive than our sun.
Is that the largest black hole we've ever discovered?
No, there are bigger ones than that, but that's the scale of them. It's a big-ish one, that. But if you think about it, I mean, so...
In a groundbreaking achievement, scientists captured the first images of black holes. The Event Horizon telescope provided a glimpse of M87 star, a supermassive black hole 55 million light-years away, and Sagittarius A star, located at the center of our Milky Way. These images confirm predictions made by Einstein's theory of general relativity over a century ago.
There's a number, it's called the Schwarzschild radius of the thing. So if you took our sun, which you can fit 1 million Earths inside, and collapsed it down to make a black hole, it would form a black hole when it shrunk within a radius of 3 kilometers, about 2 miles. So you've got to take this thing, which is what? So you squash it down till it's about 2 miles, and then that would form a black hole.
Wow.
The 6 billion times the mass of the sun means you multiply that by 6 billion.
Stars live for billions of years. These colossal furnaces, balancing gravity's inward pull with the outward force of fusion, shine brilliantly through the ages. But even the mightiest run out of fuel. And when they do, nature reveals something extraordinary. When fusion ceases in the core of a massive star, perhaps 20-30 times the mass of our sun, there's nothing left to push back against gravity. And so, in an instant, the star collapses. Not gently, not gradually, but catastrophically. The outer layers explode outward in a supernova, an explosion so bright it can outshine an entire galaxy. But at the heart of the chaos lies something far more mysterious. The core implodes, crushed to unimaginable density. If the mass is great enough, not even the degeneracy pressure between neutrons can halt the collapse. There is no surface, no solid crust, just gravity overwhelming everything. And then, a black hole is born. A place where gravity is so intense, even light cannot escape. Time and space are twisted beyond recognition. To us, the event horizon is a boundary. To the star, it's the point of no return. If you were to watch from afar, you'd see the collapsing star freeze just above the event horizon. Time, from your perspective, would almost stop. But for the matter falling in, there's no pause. It continues inevitably toward the singularity. At the center, hidden from our view, lies the singularity, a point where the known laws of physics break down. Density becomes infinite. Space-time curves infinitely. It's a place we cannot yet understand. But perhaps, one day, we will.
That's it. So that one there, that's the M87 black hole. So what you're seeing there is the emission from the material that's swirling around it. It's called the accretion disk. So you have material that's orbiting very fast, emitting a lot of radiation, and that's what you see. It's a flat disk, by the way.
In the heart of many galaxies lies a monster, a black hole, invisible and silent. But surrounding it, glowing brightly against the darkness, is a cosmic masterpiece, the accretion disk. This disk is not solid. It's made of gas, dust, plasma, torn from nearby stars, shredded by gravity, and pulled into orbit around the black hole. The material spins faster and faster, creating friction as particles collide. That friction generates unimaginable heat, millions of degrees. The result? a radiant luminous ring that can outshine entire galaxies.
In a sense, it was what's wrong with Stephen Hawking's calculation, which is a weird thing to say sometimes because people think Stephen Hawking surely didn't get his math wrong. But he did actually in his calculation. So what he calculated back in 1973, 1974 is that a black hole, so we picture this thing from which nothing can escape, even light. So when you go in, you're gone, basically. What he calculated is that even though these things are just a distortion in space and time, that's the description of them. So it's almost as if there's nothing there apart from a distortion in space and time. He calculated that they glow, so they have a temperature. So they emit radiation. It's called Hawking radiation. And he calculates how they glow. A very low temperature, but they emit things, which means that they shrink because they're emitting stuff, and so they're shrinking. So that means they have a lifetime. So first of all, one day they'll be gone. So that means that you have to address this question of what happened to all the stuff that fell in. And his calculation said that there's no record at all of anything that fell in all this radiation that's come off the black hole. So it's purely information-less radiation. So what that means is that black holes destroy information, according to that calculation. And that's a big deal because nowhere else in all of physics does anything erase information from the universe.
Stephen Hawking proposed that black holes emit radiation, now known as Hawking radiation, leading to their eventual evaporation. This raises the information paradox. If a black hole disappears, what happens to the information about the matter it consumed? According to Hawking's calculations, this information is lost, challenging the fundamental principle that information cannot be destroyed.
So it's really true that if I got this notepad and pen, right, and I wrote some things on it, and then I set fire to this, even just incinerated it, put it in a nuclear explosion, whatever. In principle, according to all the laws of nature that we know, if you collected everything that came off, all the radiation, all the bits of ashes and things, and you could just measure it all, then just in principle, the idea is you could reconstruct the information.
Imagine tossing a book into a fire. The pages vanish, the cover curls, and the words, gone. But are they truly lost forever? According to the laws of quantum mechanics, the fundamental rules that govern everything, information cannot be destroyed. Even if matter is burned, crushed, or shredded, the information about its original state is always preserved in some form. But black holes challenge that law. When something falls into a black hole, a planet, a person, even a photon, it vanishes behind the event horizon. We can't see it. We can't get it back. And, as Stephen Hawking once argued, the information disappears. In the end, black holes may not be the destroyers we once feared, but the keepers of secrets. They force us to question what we know about space, time, and reality itself. And if information can never truly be lost, then even in the darkest corners of the universe, there is memory. Perhaps in understanding black holes, we are not just exploring what lies beyond the stars, but what it means to truly know something, and to never let it go.